In this video, we will go through an example of Raoult's law when you have two volatile liquids instead of just one. So you'll notice this is very similar to in the last video we did a solution with a non-volatile solute and water. And this one we're going to just do something really similar, only you have now two volatile solvents instead of just one. And so the question is, what are the mole fractions of each, and what is the total vapor pressure of the solution? And so unlike the last one where we had to go and look up the values for the vapor pressure of water and the vapor pressure of ethanol, here it's already given to us. So our first step is we need to figure out mole fractions. And so for mole fractions, start with our 100 grams of water. And we're going to convert that 18.02 grams of water in 1 mole of water. And get our calculator out here. 100.0 divided by 18.02 is 5.549 moles of water. And if you watched the previous video, you should know that already because it had the exact same amount of water in that example as well. This time we've got 25 grams of ethanol. Ethanol C2H5OH. Mole mass of that is 46.08 grams in 1 mole. And breaking out the calculator again, 25 divided by 46.08 to 4 significant figures, 0.5425. Moles of ethanol. So, like we did last time, we're going to need to add these together to get the total amount of moles. So 5.549 plus 0.5425, 3 decimal places, 6.092 moles in total. And so the mole fraction of water would be equal to 5.549 moles of water divided by 6.092 moles total. 5.549 divided by 6.092, 0.9109. The mole fraction of ethanol is 0.5425 moles of ethanol divided by 6.092 moles in total. Point 5425 divided by 6.092 to 4 significant figures as well, 0.08905. Now, we could have also figured this, since this is a two-component solution, we could have also come up with the mole fraction of ethanol was equal to 1 minus the mole fraction of water. Since that's the only other component, we would come up with 0.0891, which for most intents and purposes, we're going to get pretty much the same answer here. So this is a way to save you a little bit of time. If you know that you have two components or even three components and you've solved for all of them except for one, you can use subtraction to figure out the missing component. Getting to the problem at hand, the total pressure is going to be equal to the mole fraction of water multiplied by the pressure of water plus the mole fraction of ethanol times the pressure of ethanol. Now that we know what those values are, we can start to put them in. Mole fraction of water is 0.9109. Its vapor pressure is 23.8 torr. And we're adding that to 0.08905, the vapor pressure of, or excuse me, the mole fraction of the ethanol, and 58.7 torr, the vapor pressure. Let's start putting some numbers to this. 0.9109 multiplied by 23.8 to three significant figures would give me 21.7 torr. .08905 times 58.7 to three significant figures would give me 5.23. And so put that all together, and the total pressure to one decimal place, because this is our fewest number of decimal places, 21.7 plus 5.23 would give me 26.9 torr. Now, just in case you were curious about does this subtraction method give us essentially the same results, we can just prove it here. 0.0891 multiplied by 58.7 would have given us the same 5.23 torr. So subtracting or doing the fraction, it's not going to make a significant difference. Yes, the numbers here are a little bit different beyond where we rounded, but in terms of to where we rounded, we would have gotten the same exact result. So what we'll find is that when we have multiple volatile components, what we'll find is that the value of the solution is going to be somewhere in between the two values. It's going to be between the high and the low. So how much, which way it's influenced, depends upon those mole fractions. So since 91% of the moles were water, we see that the solution vapor pressure is heavily shaded toward the water compared to the ethanol. If this was reversed in some kind of way, then we would see that it'd be a lot more shaded toward the ethanol. So that's how you handle these kinds of problems. Now, an interesting use for them is actually in something called fractional distillation. And in fractional distillation, what we see is we use these boiling points and these vapor pressures to actually start to separate the components of mixtures based upon their volatilities. And so the things that are more volatile tend to get separated more easily. The things that are less volatile tend to get separated a little bit more with a little bit more heat. And a fractional column like this actually can help to separate them into those components. And so what we see, this is actually a crude oil distillation pump. What happens here is the crude oil is pumped in, it is heated, um, and the fractioning tower actually heats at different temperatures along the way. And so at near the top of the tower, the temperatures are not nearly as high. And so the things that are the most volatile will go there. And so that's where we can get our liquefied petroleum gas. That's where we can get our gasoline. At slightly elevated temperatures, we get our kerosene, our jet fuel. At slightly higher temperatures, we'll start getting oils. And then the stuff that doesn't burn off of the crude oil, the asphalts and the tars, eventually fall to the bottom here and begin to get pumped out that way. So that's our discussion of Raoult's law and vapor pressure. What we'll start to look at on our next video is going to be what happens when those solutions, instead of volatilizing, what happens when they start to experience other phase changes as well. And so that's another subject for another day. Until then, take care.